when they were conducting search and rescue operations for that, well, now sadly discovered imploded submarine near the Titanic, numerous people were asking, why doesn't the sub just send out a radio signal with its GPS location? That would make the search so much easier. Well, that question is actually quite understandable, because if you look at movies and TV shows...
Right here, stand by. Royal Navy calling London G2, come in London.
Colonel Wembley, we've just made contact with the sub.
It seems that submarine communication is real easy. Well, it turns out it isn't, and what we're going to do is start off with an experiment showing why. So for my submarine, I'm going to take my old cell phone and put it in a Ziploc plastic bag. And if you decide to copy this experiment, be sure to use a good plastic bag, because I'm not going to be responsible for any dead or dying cell phones. As a simulation of our ocean, we'll fill a Pyrex cooking container with water. It's probably about 1.5 inches deep or so. And now we'll submerge our cell phone into it. And if you look carefully, you can see that we still have 5 bars. Well, that's because the water is fresh water. Now we'll do a better simulation of the ocean and add some salt. And after the salt dissolves, you can see the bars begin to go down, and from the 4 or 5 that we started with, now we probably have around 1 or 2 or something like that. So clearly the communications with the cell phone has gone down. And the question might be, why? Well, the first clue is, if we use a voltmeter and stick its probes in the salt water, we can see the resistance of the water between the probes is somewhere around 20K or less. And it seems to be less when I move it around, and I think it's because there are hydrogen and oxygen gas bubbles forming on the probes as they split apart the water molecules. Now if we take those same probes and plunge them into some fresh water, well, sort of fresh water from my well, it has quite a few minerals in it, the resistance we measure has gone way up, probably more in the 100K range or so. And that's really the clue. The salt water has a much greater conductivity than fresh water, and that conductivity has a severe impact on the propagation of radio waves for the cell phone or GPS or anything else. That phenomena is called the skin depth, and it's why it's really so hard to communicate, at least with radio, with submarines. And we should take a quick look at skin depth. Let's draw a little picture. Here's the surface of the ocean, nice and wavy. And somewhere underneath, here's our submarine with its little tower, and who knows, maybe a snorkel, and maybe that snorkel even has an antenna. And then over here, there is an island, and let's imagine there's some sort of a lighthouse on the island, and well, like everything these days, it has a radio mast and probably has even a cell phone antenna on top. And what, of course, we would like to do is get a sense of, well, if the cell phone tower transmits some signal and it hits the ocean and then deflects down and hits the submarine antenna, what will the submarine get? It would seem simple, but the unfortunate truth is that the salt water in the ocean, as we saw in our little experiment, is a really strong attenuator of radio waves. And it attenuates radio waves because of something known as the skin effect. And the skin effect is what happens when you have radio waves or electrical energy impinging on and trying to get into something that's a conductor. And the ocean is, well, a good enough conductor to make it a problem. And there's a very standard skin effect equation, which is normally given in the form of currents, because we're normally considering currents in wires and things like that. But the equation is, we take the current density at the surface of the conductor, at the surface of the ocean, and we're going to calculate the current density at some distance down. And the equation looks like this. It's the surface current density times E, which is Euler's number, valued at about 2.7. And that's all raised to this exponent, 1 plus j. J is the square root of -1, the imaginary number, all times the distance d over what is known as the skin depth. Surprise, surprise, since I've been mentioning that all along. Well, what does all this really mean? Well, the parts that we're really interested in is E and the -1 section of it, and that part over here. And if we want to really simplify things, we can say, well, that is pretty much the same as 2.7 raised to -1 when D is equal to the skin depth. And we can actually take that a bit further and say, well, this is the current you would expect at a certain depth in the conductor. Well, that current is being pushed by the voltage, so it's essentially the same as the voltage or electric field of the waves you'd expect. Or for that matter, current being analogous to the magnetic field, it could also be considered to be proportional to the magnetic field. So this number over here, which turns out to be about 0.37, is the decrease in electric field or magnetic field you get when you are 1 skin depth deep. And if you remember some of the power equations, well, power is proportional to voltage squared, or for that matter, current squared. And if we square this and we convert it to dBs, because we generally talk about radio signals in dBs, we find out that this amounts to about a 9 dB power loss when we go down to a depth of 1 skin depth. And what is 9 dBs? Well, that's approximately equal to 1/8 of the power. So that sort of put things in perspective. And I guess the only thing that's missing is, well, what on earth is this skin depth? Well, skin depth varies depending on the material and depending on the frequency of the radio waves. And we can make a nice little graph showing that. And, well, maybe we should start out with frequencies. We'll just look at 1 gigahertz, and we'll also look at 1 megahertz and 1 kilohertz, which is now getting to be a very low radio frequency. We never normally use that. And even lower, 1 hertz, so that's even below our power transmission frequencies. And the skin depth is, well, at 1 gigahertz, 1.5 centimeters or so. So what that says is if our sub is about 1.5 centimeters below the surface of the water, we're going to lose about 9 dBs in power. Now, if it is twice that distance or 3 centimeters below the surface, we're going to lose 18 dBs. Well, it turns out that very quickly you lose so much that you get virtually no radio signal at all at 1 gigahertz. And just to point out, 1.5 centimeters was about the type of distance I had the cell phone immersed in the water in the Pyrex dish. In fact, I was very carefully trying to hold it above the bottom so it was about 1.5 centimeters above and below the cell phone so I could show you some attenuation. Well, at around 1 megahertz, the skin depth gets a bit better. It's around 28 centimeters. And, well, that's beginning to get interesting if you were maybe a cell phone, maybe held by a human, but still not very useful if you're a submarine. At a kilohertz, and that's probably about the frequency of my voice or something like that, the skin depth for radio signals, not acoustic signals, is about 8.8 meters. And, well, that's still not very much. I mean, that's somewhere in the 30-foot type depth. Still not deep enough if you're a military submarine trying to evade the detection equipment that's maybe flying above you. So you want to go even deeper than that. Well, if we were to try something at 1 hertz, we now have a skin depth of 280 meters. Well, that's not quite 1,000 feet, but it's certainly getting deep enough that it's probably quite useful for submarines. Okay, well, that's all good and well, but what does it really mean? Well, it really means that if we want to communicate at depth, we have to use frequencies somewhere between 1 kilohertz and 1 hertz. Problem with 1 hertz is if we try and modulate it, the type of bit rates we're going to get for our text signals is, well, a really tiny fraction of a bit per second. We want to try and get the data rates up to something moderately usable, and apparently the military subs typically use things in the range of around 80 hertz, so a bit higher than the normal power line frequencies, and that's probably to avoid interference from all the power grids. And so that's apparently what most Navy submarines use to receive signals from their Earth stations, their ground stations, I should say. We're not a spaceship, we're a submarine. Now, the ground stations don't actually transmit from on top of a tower of any kind. They, in fact, use very long cables because the wavelengths of these frequencies are incredibly long. And we should maybe take a look at the wavelengths. Well, the wavelength in air of a 1 kilohertz RF signal is somewhere around 300 kilometers, very crudely about 150 miles or so. And at 1 hertz, well, it's 300,000 kilometers. So that's an absolutely gigantically long waveform. That's longer than the diameter of the Earth, in fact. Now, the interesting thing is in the water, it turns out the wavelength, the lambda, in a skin depth situation is actually about 2 pi times the skin depth, because the speed of these waves in a conducting medium goes down drastically. So for our 1 kilohertz waveform, we now have a mere 55 meter long wavelength. And for our 1 hertz signal, we actually only have a 1.8 kilometer wavelength. Now that's still a tiny fraction of the 300,000 kilometer wavelength in air. So how do we try and receive those signals? Well, from what I can tell, what subs typically do is drag some sort of a long antenna wire behind them, because you'd like an antenna to be at a length of something like half the wavelength. Well, probably somewhere in the hundreds of meters, you might be getting close to a wavelength of about 80 hertz. I'm not sure what it is in seawater, but even that might be, well, too long to be practical, and you'd probably have worries about it getting snagged on things, but you could probably get some decent fraction of that as your receive antenna. And now, what about the transmit antenna? Well, it turns out when you're trying to transmit radio frequency energy of any type, you really want a longer antenna, because if you try and make the antenna too short, you end up with large circulating reactive type currents that really burns up all the energy as heat. It's not a very good situation. And so what they typically do is, for the 80 hertz, give or take, transmitting station, they apparently use antennas that are 30 to about 50 miles long, so absolutely gigantic. And I guess what they do is they put them either on or slightly above the ground, maybe on things like power poles. I mean, you can just imagine having the power company put up some power lines, except using them for your special purpose. And what they like to do is do it over ground that's dry, which is really quite different from most transmitting stations. You want the ground to be dry for these low frequencies so they can go right into the ground and hopefully not only transmit through the air, but through the ground and through the seafloor and make its way to the submarine. In a normal situation, such as for shortwave, you actually like a nice conductive ground. In fact, shortwave stations are usually set up in places like marshes, so that ground acts like an electrical plate and essentially reflects the antenna sticking up, so there's a reflected one that appears to be sticking down, and it turns out to be a very good, very efficient way of transmitting radio waves, but well, not in this case. So that's sort of the situation. We end up using these very low frequencies and at very low data rates, probably in the bits per second or tens of bits per second type range, and they only really work very well, if you can call that well, going from the ground station to the submarine and not back. It also means that anything at these frequencies, like cell phones or GPS, well, is just not reachable by the submarine. Now, in practice, what submarines do is they will actually get close to the surface or even stick an antenna above the surface for short intervals to do some communications. Or apparently the other thing they do is release a tethered buoy of some kind that sits somewhere below the surface and has a small antenna just below the surface, so it can operate somewhere in the skin depth or two type range of higher frequency signals and do a bit better communications that way. But the other thing that never gets talked about is, well, when we have the signal going to the ocean like that, or for that matter coming through the ground, and there is this interface between ground and seawater or air and seawater, we actually get reflections. And I want to briefly talk about the reflected energy and how much that is. Let's once again draw our nice little picture. There's the ocean. Here's our island with the antenna, and then down in the deep blue sea is our submarine. And once again, the antenna is trying to transmit to the submarine, and what I did mention before was there are in fact reflections, and we of course expect that because, well, if you've ever been by a lake or something at sunset, the sun and its light waves reflect very nicely off the surface of water, and it turns out radio waves do the same thing. Now, we're going to start off with just thinking about reflections coming straight down, in other words, as if the antenna was above the submarine. And, well, to do that, we're going to use the standard reflection formula, which is this. The reflection coefficient is the impedance of the sea minus the impedance of the air divided by the impedance of the sea plus the impedance of the air. And you say, well, what is the impedance of the sea and the air? Well, the impedance of air, which is essentially the same as the impedance of free space, is 377 ohms. And you might be wondering, well, what on earth does that mean? Well, it is the relationship between the electric and magnetic fields, their proportions, just the way impedance or resistance is the relationship between voltage and current in a wire. And we can get the same number, the same type of number for seawater, and I found a paper, and they came up with a value of 42 ohms. And if we plug it into this equation, well, what do we get? We get a value of somewhere around 0.8, and I should point out this is the voltage reflection constant, and if we want to get power, we have to square it because power is proportional to the voltage squared. So what that means, about 0.64 times the power of the radio signal gets reflected. In other words, 0.36 times the power makes its way through. And, well, that doesn't necessarily mean very much to most of us, but if we were to take that 0.36 and convert it to dBs, that is about minus 4.4 dBs of signal loss. So, well, as we can see here, a little over half the signal is lost. So that's a fair amount of power that's lost simply by going through the surface of the ocean. Now, what we haven't even talked about is the fact that when you have the angle of incidence changing and becoming much more parallel to the surface of the ocean, you get much better reflections, and that's indeed what happens. So, in fact, this is almost a best-case situation. The other thing you might notice is I've sort of drawn it so that the wave comes in here and then goes into the ocean at a steeper angle, and that's because the speed of light or radio waves in air is considerably faster than that in the water, particularly under very conductive conditions. So we get that angle coming in quite steeply after it hits the surface of the ocean. Anyway, how does that work when we're trying to transmit back? Well, we lose probably about the same amount of power, but it actually gets worse because as our angle of incidence changes, we very quickly get into total internal reflection where 100% of the signal gets reflected back. So we really only have a very narrow window in here of angles that we can send signals out to the air. The bottom line is we lose a certain amount of power just to reflections, and if we were transmitting from somewhere on a continent and this island was the edge of the continent and some of it was going through the earth, well, we'll get some sort of a reflection from the earth to water boundary. It might be somewhat less than our worst case scenario here because this will be more gradual, and if the boundary is gradual it can sometimes reduce the amount of reflections you get back. Unfortunately, because the wavelength is so long, even if this is a rather large boundary, it's still pretty small compared to the wavelength. Anyway, so that is the other half of why it's so hard to send radio signals to and from a sub, and why that poor stricken sub couldn't have a GPS on board to know where it was because it couldn't get the signals from the satellite, and for that matter couldn't then transmit them and say, hey, we're in trouble, here's our location. So how do we communicate with subs? Well, what that stricken sub did have was some sort of an acoustic or ultrasonic modem. And acoustic or ultrasonic, well, ultrasonic is simply acoustic or sound waves at frequencies higher than we can normally hear. And depending on how old you are, most humans can hear up to somewhere between 10 kilohertz if you're old and 20 kilohertz if you're young. So that boundary between the two actually varies a bit. Anyway, submarines apparently typically use anything from 3 kilohertz to 30 kilohertz acoustic waves, and they modulate them just the same way we modulate radio waves. So you could do it AM, FM, various other forms of more modern modulations. It doesn't really matter. Unfortunately, what typically happens, particularly with things like acoustic transducers, is you end up with a very small bandwidth compared to the actual frequency that you can transmit signals on because of resonances. So if you have a signal at 3 kilohertz, it doesn't mean you can use the whole 0 hertz to 3 kilohertz bandwidth, probably more like 10 or 20% around 3 kilohertz, or at 30 kilohertz, maybe 10 or 20% around that. The bottom line is the data rate is generally way less than the frequency of the carrier signal. And so I would sort of expect down here we're probably, if we're lucky, in the tens of bits per second, and over here maybe somewhat more than that, depending on how much error correction we have. And typically what you'd end up with is lower frequencies and data rates for longer distances. And from what I heard, that sunken sub had very low data rates when it was at depth, so even texting was hard. So we're probably talking about somewhere around a few bytes per second, which at times may be all you really need. But there's a much more interesting way that people are looking at now for communicating with subs, and that is blue light. And the reason blue light is interesting is, well, if you've ever scuba dived or seen some movies using the natural underwater light, when you go down more than a few tens of feet, you start noticing that the light that trickles down from the surface is very blue, and that's because the ocean water is absorbing all the reds and longer wavelengths of light. Blue gets through rather nicely, so people have had the ideas, well, maybe what we'll do is we'll take a laser and we'll point its beam at the sub, and hopefully because blue gets through, we can send some data. And with light, well, we already are used to sending light with data in things like fiber optic cables. You can get very high data rates, and you can get such high data rates because light itself has extremely high frequencies, so getting kilohertz or megahertz or even gigahertz of bandwidth is really more limited by what we use to modulate and receive the light signals than the light itself. What you would certainly expect to happen is as you pass it through the ocean, the signal scatters, and probably the real downside of using something like a laser beam is you have to know where the sub is and point it to the sub. And, well, that requires some prior knowledge. But the other thing that sub use is apparently underwater communications points. And what they do is they apparently have underwater cables, and at certain locations they have some sort of a module that either has an acoustic modem or alternately some sort of blue light system, and the sub can get near it and establish a communications link that, because, well, it's so close by, can be at much higher data rates than you otherwise would, and you can probably transfer large amounts of data back and forth. So that's a very quick discussion of communicating with submarines and why it's so hard for a sub to communicate and get signals from GPS satellites and so forth. Now, I should point out that we're actually quite familiar with acoustic signaling underwater because, well, if you've ever seen an old movie with a submarine, inevitably what you hear is the classic pinging sound of the old analog sonars.
One ping only.
We use things like that today, particularly in black boxes on aircraft, so that if they end up in the ocean, one can listen with microphones either on the surface or in submersibles and try and locate those black boxes somewhere in the murky depths of the ocean. Well, that was a very brief introduction to communications underwater. If you want to try the experiment, an even better way of doing it might be to use something like an aquarium, so you have a greater layer of water on either side of the cell phone. Now, if you're doing that, you might have to start with distilled water because it has an even higher resistance than the mineral water from a well or the chlorinated water from a city water system. And you really want to see that difference between all the bars and a few bars, and starting with distilled water should give you a few more bars at the beginning. Anyway, when you do that, then add some salt, and of course make sure there aren't any fish in the fish tank, because I don't want to be responsible for the death of thousands of poor fish. But hopefully you'll be able to see the bars go down, and that's a very good illustration of communications with submarines and the skin depth effect. I hope you found this video interesting. See you next time.